you see, this is going to be a presentation about a code called PyNucleus, and that is a finite element code for general non-local problems. So what are these problems, or what are the operators that we consider here? Well, I mean, this might look fairly familiar to most of you, but let me just repeat that. So we have some horizon parameter delta, and in our code, this can either be finite or it can be infinite. And we have a corresponding interaction domain. So if we have our domain of interest where we want to solve a problem omega, then the interaction domain is essentially the color of size delta around that domain. And when delta is infinite, well, then it's the whole complement of the space of the domain omega. Now, the operator that we are looking at takes this particular form here. It includes quite a lot of different operators that you find in the literature. So arguably the simplest maybe is the so-called integral fractional Laplacian. So in this kernel, we have a sort of normalization coefficient that's going to be a constant then. We have a singular part in the case of the integral fractional Laplacian that is just some constant power of the difference between the two evaluation points. And the horizon for the integral fractional Laplacian is infinite. So effectively, this term here in the back just drops out. But there are obviously also a lot of other operators of interest. So people have considered tempered fractional Laplacians, where you include a prefactor that is an exponential. You can do truncated fractional Laplacians, where you then essentially chop off the tails of this kernel. And more recently, what we started working on are fractional Laplacians with varying order. So both the type of the singularity can vary over your domain, depending on x and y, and the sort of diffusion coefficient or normalization term in front can also vary over your domain. And finally, you can obviously also consider kernels that are integrable. So what we have implemented in our code is, for example, a constant kernel, where we don't have any singularity here, or something we term a peridynamic kernel, where we just have the inverse of the distance between x and y. Now, for now, what we make in terms of assumptions is that the kernel is symmetric. We have some implementation for non-symmetric kernel, but that is not yet part of the released code. And in most cases, the interaction domain should be defined with respect to the true norm. We have some preliminary support for other norms and other shapes of interaction, or not interaction domains, but of the sort of the action region of the kernel. But the most well-tested, obviously, is the two-norm ball. All right, and so what is this code? It's written in Python, but in order to actually get decent performance, a lot of the computationally expensive kernels, and well, kernels in this computational sense, not in the non-local sense, they are compiled to C via Python. But what that means is that this is all in Python in principle, and you can use it directly from NumPy and SciPy. So there's a nice compatibility if you want to integrate this into some other code. What we support so far are meshes in 1D, 2D, 3D. 3D is in brackets because we don't yet have the non-local assembly pushed for that. We can do uniform refinement, have some boundary snapping for that. We also do mesh partitioning and repartitioning using meters and its cousin parameters. In terms of finite elements, we have discontinuous P0 and then family of nodal Lagrange elements. And what we also provide is assembly of local differential operators. So if you want to implement a whole model that has sort of a combination of some local and some non-local operators, you can do that. We provide several sort of general purpose solvers for these problems. But in particular, we also provide a geometric multigrid solver, which for these elliptic problems works really quite well and gives good solve performance. The computations can be distributed via MPI. And for the operator assembly, you have several different options into what sort of object you want to assemble your your non-local operator. So if we look at this weak form here, obviously, in principle, this could be a fully dense matrix. But the first option, what is our target for assembly, is just a simple sparse matrix. So when the horizon is somewhat similar or an order of magnitude of the mesh size, then it might make sense to assemble into a sparse matrix. But obviously, as the horizon gets bigger and bigger compared to the mesh size, at some point, you'd rather assemble into a dense matrix. Now, obviously, that has certain issues. So if you think about the dense matrix, you'll have at least order n squared complexity in, well, for something simple as a matrix vector product or even in memory. So as an alternative to this, we also provide hierarchical matrices. So in a nutshell, what it essentially does is that it applies a approximation of matrix blocks that are on the off diagonals. And by doing that, you obtain then a quasi-optimal complexity for both the assembly and the matrix vector product. So it scales more like order n log n. What it means is that effectively you can assemble and solve these non-local problems in the same complexity as your usual classical PDE problem. Furthermore, I should say that especially for the fractional kernels, we've spent quite a lot of time tuning the quadrature orders that obviously have to depend a little bit on the relative location of elements in the mesh. So if you have elements that are very far apart, you can obviously go with a very low order quadrature order. But if you have elements that touch each other, you have to even use a specialized quadrature, and you have to tune that quite well so that you don't spoil your overall discretization error. So we've spent quite a lot of time on that. Now, just to give you sort of the minimal example of what it looks like to solve a problem using PyNucleus, it's really quite simple. So this is 20 lines to solve a fractional Poisson problem. So we ask to get a fractional kernel. We want, say, on dimension 2, and we want a constant fractional order in this case and infinite horizon. We get a mesh with a given mesh size. We have to specify which kernel we're using and what sort of boundary condition we want to use. This is important because if we don't specify that, we don't know if we need to actually mesh the interaction domain or if we can skip that step and actually only create a mesh for our computational domain omega. Then we build a finite element space over this mesh. In this case, it's a P1 finite element space. We get an analytic function that in this case is just a constant. And then we assemble our different operators and vectors. So we get a right-hand side vector, we get the operator. We always have to pass in the kernel, and we also tell PyNucleus what sort of matrix format we would like to get. We build a solution vector, and then we just also get a solver for this problem, solve it, and then plot it. Now, this is sort of the minimal problem. You can obviously pass in your own mesh or your own degree of freedom manager if you want to integrate this code into some other application. I should also say that the documentation for the code contains a couple more examples that have a lot more detail than this sort of short and minimal example. And we also include some of the sort of more advanced drivers into the repository, so you can solve some other problems as well with that. Now, in the past, what have we used PyNucleus for? Well, we have obviously solved quite a lot of Poisson problems. We also did some mesh adaptivity with this code. You can solve time-dependent diffusion problems. We did some reaction diffusion systems with this. Can be used for Helmholtz problems. We did some Kern-Hilliard and Alan-Kahn. We also did some optimal control problems. That was both optimal control for source terms, but also the learning of optimal kernel parameters. And more recently, we started looking into non-local interface problems and coupling. I should mention the largest problem that we've solved with this code to date, and that is for infinite horizon, so not some sort of small horizon, which makes solving large problems easier. But for infinite horizon, there's about 2 million unknowns. And I just quickly computed how much that would be if you were to assemble this in a sort of dense matrix format. That would be about 30 petabytes. So that you really need the hierarchical matrix approximations in order to solve problems of that size. Now, I should also say that this is obviously a research code. It's under active development. But what it also means is that some things might not work as expected. So if you happen to actually want to use this code and something doesn't work as expected, please let me know. I'm sure it's not your fault, but mine. Now, with that, here are the links for the code and the documentation and examples. And I also want to acknowledge the funding that made this project possible. With that, thank you, and I hope there's questions.